Good evening. My name is Graham Smith. I'm an assistant professor here in the physics department. It gives me great pleasure to welcome you here this evening to introduce tonight's speaker. But before I do, I want to take a few minutes to give you some background to this event. So this public lecture is part of the Boulder Summer School for Condensed Matter and Materials Physics that's held annually at CU. The director of the school is my colleague Leo Rezakowski right here. We invite 65 of the brightest and best PhD students and postdoctoral researchers to attend a 4-week set of lectures delivered by world experts in the annual topic of the school. This is the 19th school. Past schools covered diverse sets of topics from superconductivity to biophysics. The school is supported by the NSF, National Science Foundation, and the University of Colorado. So this public lecture is an example of your tax dollars at work, and we certainly appreciate the support. This year's school is on a very exciting topic of quantum information. Quantum information is the exploration of what happens when information processing meets quantum mechanics. And in the past 25 years, we've learned that quantum effects could give really big advantages for communication and computing. More recently, we've seen in past years impressive progress towards building devices to actually realize these promised advantages. Today's speaker is DiVincenzo, Professor David DiVincenzo, who's a world expert on quantum information. He got his PhD from the University of Pennsylvania in electrical engineering, and after a postdoc at Cornell University, he joined IBM Research, where he stayed for 25 years. And his work there on quantum information and computing, starting in the 1990s, helped establish the foundations of the field. David's work is characterized by a really inspiring mixture of practicality, optimism, physical intuition, and mathematical rigor. And it's had a huge impact on the field. So, for example, his papers have been cited by other scientists over 47,000 times. Since the year 2011, David's been Alexander von Humboldt Professor at RWTH Aachen University and Director of Theoretical Neurosciences at the Jülich Research Center, where the work he's doing continues to deepen our understanding of and enthusiasm for quantum information. So without further ado, please join me in welcoming David DiVincenzo.
Thank you very much for that rousing introduction. I'm told it might be work without any amplification, which is fine with me. I think you'll all be able to hear me. It's a splendid room for giving lectures, so there's no need for microphones. And you'll see examples.
You'll have to speak up.
You would like me to speak a little longer, slower? I should speak forward to the audience and with a good pace. Is that what you advise?
Or use the microphone.
This was technically not permitted this evening for some reason, some exclusion principle or something. Okay, but let's give it a try. I hope I have a very nice accent, so I hope that I'll be able to be clear to all of you. So tonight I have a story of several different threads that I want to carry you through, and I have this sort of prosaic starting slide just to orient me and you. I'm going to be talking about computers, and my own expertise is in quantum computers, and we'll get to that at the end. But mostly I want to tell you the story of the journey there, rather than where we are today. Or I'll tell you only at the end the story of where we are today in quantum computers. But I want to talk for quite a while about computers in general, and about the very interesting, I guess I'm about to get mic'd. Okay. Put this in here, and this somewhere or other. Okay. Okay, now I have to tone it down to get a little more sort of lounge act. Okay, so we'll hear. Okay, so I'm not going to install the newest update of Skype. Let's see. Oh no, but it doesn't show up here. That's very good. Okay. So So I want to tell the story of how computers in general have renewed themselves again and again and again, and how we foresee a next renewal from the quantum direction. But I'll tell you more generally how this progression and the move to new technologies and new models of how to approach computing. Computing is also a business, and it's also a whole economic model, and how that's changed over time. But how physics has really played a big role in enabling these progressions from one style of computing to another, one approach to computing to the other. But I wanted to reach also far back before the history of computers and tell the history of the bit, so how we get zeros and ones. And this is a story of physics, about how physics gives us new means of embodying things which are either zeros or ones. So I want to talk about dichotomies in physics, the long history of the bit. And this will mix together with what we mean by the quantum bit, and that will be quite a bit of a shorter history. And if I've managed to knit all of these threads together, I hope that you'll have an idea of what this new machine is and what it involves, what people are doing in the laboratory when they say they're making a quantum computer, and what it will need to put quantum things to work. Here's one of the prime quantum engineers here, banged up, but he got here. So I also wanted to say that I don't know if any of you know the book. Maybe I'll even ask you, but my title is ripped off from a very nice book, and I have a little bit of summer reading recommendations if you want. And the book that I'm referring to is Soul of a New Machine, not Soul of a New Quantum Machine. Soul of a New Machine was a book written in the 1980s. Sorry, I have a small display problem which I'm trying to solve. Okay. It means I have to turn around and look at the screen a little bit. So anyway, this is the book that I'm referring to. How many of you have ever seen and read this book? Okay. Very good. Goodly number. Okay. So you know, so half of you or so know about this book and know that it tells the story of the development of a new computer in, I think, 1981. Yes. Which was, a great machine for its day, and it tells not really the technical story, although there is a technical story behind it. There were developments of chips at that time that made this new style of computer possible, but it's actually more of a human story. It's a story about the people who had to go in and get together and know the technical facts, but also how to do a complex thing, how to put together a complex new thing, new technology. A new thing that could work in the market, could actually do important computations, and be of value in the world. And the thing of value that they created was this machine. So it was the Data General Eclipse, and it was a new style of computer at that time called a mini computer, and it was definitely transformative in its day. But I bet that none of you have. Well, maybe some of you older ones of my age have ever touched a Data General Eclipse. Yes, a few. But probably none of you under the age of 40 have ever touched or even so much as heard of a Data General Eclipse. Because, well, maybe the brand name Eclipse was maybe an unfortunate choice because it's sort of been eclipsed. That we don't think mini computers are so sexy anymore. This is the front panel of a machine that was about 2 filing cabinets of size, and it did computations, but it's about the computations that you can now do on your iPhone. And so indeed, the great efforts, which were brilliantly documented by Tracy Kidder in this great documentary style book, have gone in this way. I thought maybe this is an interesting thing to see. So this was the nice logo of Data General, and they had their machine, and they kept going for a while, but eventually they were gone, and they were swallowed up by EMC Corporation. Now, I bet not many of you even know what EMC Corporation is, but they were an important manufacturer at one period.
but they're gone too, and a few years ago they were swallowed by Dell. And I think there's another fish coming along, and Dell's not doing so well, but at least many of you at least know the word Dell, you know that it's a computer, and they sort of inherited by this succession the knowledge that was, among the engineers and the scientists of the data general era. And I think in the end, we're going to have a succession like this in the quantum world as well. I think these successions are good, actually. I mean, they're destructive, they're disruptive, but they're kind of necessary, in fact. And I wanted to kind of tell a story of what can go wrong with these sort of things by going to a story which comes from sort of personal experience of my own. So I grew up in Philadelphia, in West Philadelphia, and the neighborhood where I lived was a hotbed of industrial activity. So when I was very young, I saw the site of this factory, which was the factory of the Grill Company. I mentioned a few pieces of history about that. There was an immigrant from my part of the world, my current part of the world, Johann Grill, and soon after he came to Philadelphia, he started a factory to build streetcars. And at one time, at the time of this Currier and Ives picture, around the turn of the 20th century, this was the biggest streetcar factory in the world. And I could go and look at it when I was young. It made machines like these, which I was also quite familiar with in my youth. I don't know, are any of you from Philly? A handful. So maybe you remember these. These were, actually, this was the thing that I always thought was the Brill product. This is the old trolley that I would take to high school. They actually built, at that era, the trackless trolley, which you would see in various neighborhoods in Philly, but not in my neighborhood. They were in South Philly.
Media still has a trolley.
They still have trackless?
Media still has a trolley that goes into 69th Street.
Okay. So these trolley, I mean, there are still trolley lines in Philadelphia. But actually, Brill wasn't doing so well. They were still only making this product, I think, at one time. And, you can see it's not a really attractive product. You can see the air conditioning system, for example. It's not really high-tech, and it wasn't in my day either. And in fact, around the time, when I was very young, this factory closed. In fact, the Grill Company was liquidated. And so this whole big site, according to the rules of succession, could have been, put to some other use. But I have to say, because of the way Philly is, or whatever, the pace of economic development wasn't so fantastic. And so this is basically the way I remember it when I was young, and it's still the same way basically to this day. They've never redeveloped the Grill site, and they've never, this sort of painful progression of economics, of putting something new in its place hasn't happened. So I think this is a kind of cautionary tale that people who plan development of science and technology generally have in the back of their mind, that they don't want this to happen. They want new stuff. And I can see for myself, policymakers and politicians, they're really desperate for new stuff. They don't want their cities to look like that. They want to look like, making the next fancy, interesting stuff. And recognizing that after another 10 or 20 years, it's going to be other interesting, fancy stuff. Okay, so now I get to some thoughts about, I want to bring together some stories that have made this new quantum idea possible, the new idea of making technologies out of quantum things possible. And there are many ways to start this story, and I decided to focus on the sort of simple fact that to make quantum things, you have to make things very cold. And there are many ways to make stuff cold, and if you go out in the Hall of Fame here in the corridor, you see some of the ways that people in this science department, in this physics department, have made stuff very cold and have gotten Nobel Prizes for it, for Bose-Einstein condensates. I wanted to start with something much further back in time that in some sense is more relevant or the coldness that is needed or is actually in use for the quantum computers that are being made today. So, and this is somewhat where I thought, well, it'd be great if I didn't have a microphone, because then I could do lectures just like these were made. This is a lecture by Sir James Dewar, and there he is. He's demonstrating for an audience in 1904 some of his new discoveries, which were how to liquefy gases. So he's actually doing some demonstration involving liquid hydrogen in this picture, because that was his claim to fame, that he had found out how to take the gas, hydrogen, and make it into a liquid, and thereby achieve a very low temperature. But I got this rather elegant-looking picture, and you saw it maybe in the advertising of this lecture. The poster maker, I didn't have anything to do with put some other posters in the back wall, so it was a little bit faked. The actual posters were, pictures of the stills and the apparatus that he had to put together in order to liquefy the hydrogen. But there's another rather scary tale when you read this, that this is also a little bit fake news, that this is an embellished enactment. It says that there were people put in the audience who weren't actually there because he wanted to please some patrons. Actually, of course, if you know the history of medieval art, that has a very long tradition anyway. Actually, one of the people that, well, I won't get into that, but so it's a little bit of a fake, but it was indeed a real event, and it's actually show a couple of more pictures of this particular lecture hall, because somehow it comes back in the history of science that there's a lecture hall in London at the Royal Institution, which has been very instrumental in bringing new developments in science to be told to an audience. So I still feel some kinship to these rather famous events in the history of physics. So he was liquefying hydrogen, but as I said, this lecture series had a long tradition. This was 50 years earlier. At the same desk, Faraday, who discovered many of the laws of electromagnetism that are also very important in our quantum computing work, he was lecturing. Actually, somehow the audience was pretty different in the two cases, but somehow the science had gone way upscale in 50 years. You actually see some real working people in the audience, and the ladies in their bonnets and so forth, rather than ladies only in their sort of opera clothes. So anyway, but I'm going to put that on hold a little bit, because I want to take up another thread, which will bring it together, which is way, way further back in time. And I could say this is another one of my summer readings, but maybe I wouldn't recommend it unless, first of all, you're a real Francophile, because you shouldn't be able to read French to understand this story. But I'll choose this to pick up an idea of where in science we see something of a dichotomy. And I bet even the experts in the audience don't actually know where I'm going with this, of what this treatise, so this is a treatise on light, written in the year 1690 by Huygens, by a famous Dutch scientist. And I think this book is revolutionary in several respects, actually. And I've been, trying to read it. I'll say it's not actually that easygoing. It's not exactly on the summer reading level. It's more like taking your, some physics textbook and saying, I'm going to read it this summer. So I wanted to tell you a few high points of this, and I'll tell you the physical bit, which is also a quantum bit, that he happened upon, or he came upon by deduction in this work. So this is the title page, and it's like sort of old-fashioned headlines. It keeps going on and on about, this is a great thing, and it talks about reflection and refraction, and in particular, it talks about the extremely weird refraction properties of a particular crystal from Iceland. So this is the story of a study, a big chunk of this book is about the detailed study of a particular crystal. But the beginning of the book describes the latest exciting scientific development of the year 1690, which came from this other gentleman, Ola Römer, who was a Dane, who had been painstakingly doing observations of what were the sort of exoplanets of the time. So, nowadays we mean exoplanets of planets of other stars. But at that time, it was only quite recently understood that the planets have their own mini-planets, that they have their moons. And what this diagram is a drawing from this picture, from this book, shows the solar system, but just the Sun, the Earth, Jupiter, and one of its moons, and the shadow cast by Jupiter. And what Römer had been involved with was painstaking studies over many years to measure the eclipses of these moons, of the large moons of Jupiter. And he had been timing them. And this is rather, well, it's painstaking work. Not very exciting on the face of it. But he found that the appearance of eclipses were rather, well, at first irregular. The timing of when these moons would disappear in shadow and then re-emerge out of shadow. But he found that he could correlate it with where the Earth was on its orbit, and would be delayed or advanced depending on whether the Earth was further away or closer in. And so the hypothesis that was only quite tentatively advanced by Römer was that light travels at an actual velocity. It was not at all clear to thinkers before that light, actually traveled in any normal sense of the word. And it was actually Huygens who took up this data and said, clearly and loudly to the public, it means that the light travels just like a regular wave. It's just that it's stupendously fast. And the deductions that were extracted from these observations was that light would traverse the orbit of the Earth in about 22 minutes. So it's not quite right, but they got the right ballpark. And which was incredibly fast compared with anything you could even imagine. So, but he concluded from that, well, light travels really fast, and that it would therefore travel out in spheres. That is, it would an impulse of light would travel out in an ever-expanding sphere. And this was really the key, initial thought of Huygens, that light travels out just like regular waves, but it has wave fronts. Now, he immediately understood that there were some peculiar exceptions to this, and so that's why he spent a long time thinking about this particular crystal. And I show you now a picture, a modern picture, of the crystal, the kind of crystal that he studied. And it has a feature that you have double images. And this had been known and descriptively described, but he actually studied it very quantitatively. And you have to, this is where I say this book is not a piece of cake, because then he goes through very painstaking arguments about the observations that he made. Every single letter in diagrams like this, of which there are many in the book, are carefully described. It says, please look at triangle ABC, and then consider this, and you go through pages of discussion of diagrams like this. But what he concluded was that his initial thought, which is light spreads out in spherical waves, was not true inside crystals, and that there were two things that he observed. One is that there were double images, and what they turned out to mean is that some part of the light travels in ordinary spheres, or here in projection in a circle, but some component of the light didn't. And that after long observations, he concluded that the light expanded in the crystal in not a sphere, but an ellipse. With a particular long axis and short axis. In other words, the light was traveling faster in some directions than in others. And he quite carefully showed that it is in fact in the shape of an ellipse. This I would say is an observation of a real physical embodiment of a bit. What is a bit? It's something which has two attributes, and two discrete attributes. That it's either something or something else, and it's not in between. In this case, the light either traveled in a circle or it traveled in an ellipse, but not fuzzily in between. And that when you saw an image involving those two kinds of light, it would not be some fuzz in between. It would be either this or that. So that's not only a mathematical bit; it's really a physical embodiment of this idea of dichotomy. Now, he didn't know it, and he gave it no name, but this is what we today call polarization, that the two species of light are, in fact, involving the polarization of electric fields. But none of those descriptive facts, he had no means of knowing all of these additional details, which took another 200 years. But we do use polarization to this day as an information carrier, and it does in fact form the basis of what we call a quantum bit. So I think it's fair to trace it back to this. I think what's also remarkable, actually what got me reading this book, was that it has a picture like this. And this is in the year 1690. Even 200 years later, there were many scientists who did not accept the idea that materials were made of atoms. But here he was sketching this picture, which to all appearances means that he knew that this crystal was made of little balls. I think what he says is that I don't really know, but I have to make some idea of what could be causing this. And this is actually reproduced in textbooks today. It's in Kittel, if those of you want to go look. But I think Kittel never really knew that this was not only a picture of a bunch of balls. These are actually intentionally flattened. It's just hard to see in the perspective that's shown. So it's a little bit more like a picture of like fish scales. And so he knew that whatever the sort of elementary units were, he believed that there were such things and that they were really, really small. He didn't know how small. But they had to have some non-spherical shape in order to explain this possibility that some of the light traveled with different velocities in different directions. So this is not a bad guess. In other words, the actual, composition as we understand it today of these calcite crystals, it does in fact have units that are not very symmetrical, and that's the reason why it's birefringent is the modern word for this effect in this kind of crystal. On top of all this, I'd like to say this book, furthermore, contemplated the question, how did this light get to us through the vacuum of space? They didn't quite know that there was a vacuum, but there was enough evidence to show that there probably wasn't much between us and Jupiter. And so it's this book that introduced the so-called luminiferous ether. This was a concept that you mostly only hear about it because it was a concept that got demolished by Einstein. But you're not told that it was introduced 200 years earlier by Huygens. And he understood it had all sorts of strange implications, that if he felt you had to believe there was something between us and Jupiter, and he would call it ether, but he knew it had to be, if it were a material, for example, it had to be incredibly stiff and light in order to support the waves of such tremendous velocity. But that it somehow had to interpenetrate and not interact with ordinary matter. So he got it, wrong, but it was he who set up the ideas to begin with. He set up a good, respectable idea that Einstein could eventually demolish and replace with something better. Okay, so some reading if some of you feel it. But this is not my the other item that I had on my summer reading list. For that, I wanted to go on to, I want to come back now to the story of liquid gases, of how you make, well, how you push together atoms that mostly like to form gases and push them together and make solids, or make liquids or solids, I should say. There's a nice moment in that history that I thought I'd relate, because it relates directly to the discoveries of Dewar. So just not long before, remember Dewar was 1905, I think. So 10 years earlier, there was a very small mystery in chemical physics that probably few had even noticed at that time. But Lord Ramsay, a great physicist at that time, had noticed that there was a tiny discrepancy. Here's the discrepancy. It's in the 4th decimal place between the observed density of nitrogen extracted from chemicals versus nitrogen that was extracted from air. Maybe some of you know this story. I remember I was told it in high school chemistry. He mentioned it in a lecture. It was not at this Royal Institution, but and this lecture was attended by a very accomplished chemist named William Ramsay. And Ramsay decided that he would give it a shot of understanding what was going wrong. Rayleigh was of the opinion that the chemically synthesized nitrogen was probably impure. But Ramsay somehow had the intuition that it was the other way around, that it was actually air that was impure, which sounds implausible. But so he went to work. There's some special apparatus that he had to construct and laboriously do fractionation of air, basically. And he found out that indeed about 1% of what we thought was nitrogen was actually something else, and including all the gas, between me and you, is about 1% argon. Now, the word argon, or the thought that there would be something called argon, had not occurred to anybody yet at that time. And so he processed tremendous amounts of atmospheric nitrogen and got a sample of argon, got together quite a bit of argon, and then continued to distill it further and found out it was itself consisted of various constituents. And so he, in fact, found a whole column of the periodic table. He found the neon, the krypton, the xenon, and also helium. This was a whole discovery of what was happening, or what was present in our world. First of all, by looking at very tiny discrepancies in things that were supposed to be the same. So you have to believe that these were really different. Not 1.250, but 1.257 in density. So I like to think of this story as the sort of the discovery of the dark matter of the 19th century. Because up to that time, argon, was just as dark as all the dark matter we talk about out in space. It couldn't be smelled, it couldn't be seen, it didn't have any physical effects until you tried to really tease it out. Rayleigh was able to immediately study some data. He deduced that it was monatomic, that is, that it was not in fact forming a molecule from the specific heat. Now, once these gases were available, one could immediately do these tricks that Dewar was applying and making them all into liquids. But the liquefaction was basically the same principle that used in any refrigerator that you have in your house, which is that it's pressing the gas through a nozzle at high pressure and letting it, and that causes a strong cooling of the gas. And if you do it, strongly enough, you can cause it to liquefy. And so this trick permitted all of these to be liquefied, including these brand new gases, neon and argon. Now, this story had to go further in order to be, quote, useful for technology as we see it today. These are interesting low temperatures. But the story got interesting with helium, so which involves the absolute lowest temperatures that you see on this chart. And these are all temperatures in Kelvin, so these are all temperatures above the absolute. So this kind of rapid progression, well, I have a bit of a story that, over the course of a couple of tens of years, brought the temperatures that, were available to humans from, 100 degrees or 150 degrees. I guess it was dry ice, was probably the thing that was known somewhat earlier, down to a few degrees above the absolute. So, in fact, I'm going to read a few quotes from this book, and this is one I do recommend as interesting, even summer level reading. This is also a fairly old book from 1983, but with very current messages. So this is Casimir. I know a few of you who are at school are quite knowledgeable about Casimir's contributions to science. He was a very excellent physicist. He was also a research leader at a company, at the Philips company. But he was also, he had a period in his life when he was very deeply involved in low temperature research. So when he tells in this basically autobiographical memoir, a lot of interesting stories about how that came to pass. I was going to tell that there are other dichotomies in physics which he's quite involved with. I'm going to skip, however, one little story about that and stay with the story of low temperature physics. I just jumped over the story of spin, which also has a similar story of discovery of a dichotomy by someone who was who helped Casimir at one stage in his career, a scientist named Pauli. But I just want to read out what Casimir knows. And it's a little bit nationalistic, I have to say, which happens sometimes in science. So, I had already shown this in the chart, that this air had been liquefied in 1877, and then he mentions that his colleague, or his predecessor, his countryman, is a Dutch scientist, Camerling Onnes, was trying to catch up, and he also managed to do liquefaction. But he was doing it, he was not the leader. And then Dewar started liquefying hydrogen, and Camerling Onnes hadn't gotten there yet. But he eventually reproduced the work from London. And then on the 10th of July in 1908, helium was first liquefied on Earth, and then it happened in the laboratory of Camerling Onnes, and he jumped ahead of Dewar. Yay. Here's the man I'm talking about. This is Camerling Onnes is a double last name, so it's Heike Camerling Onnes. That's the man, and he's standing in front of some big equipment, the big pump things that were used to finally liquefy even helium. He's standing next to Van der Waals, who was also a scientist at that time, and in Leiden, as it says here. And he provided the theory which guided these experiments and told the laws of imperfect gases that predicted liquefaction. So he managed that, and it immediately jumped, from the classical to the quantum, basically. That in the very first run of this liquefier, they stumbled upon superconductivity, for example, which is a fundamental, quantum effect in metals. He was seeing, but didn't realize that he was seeing something called superfluidity, which I'm pointing to the Hall of Fame here, which the newer manifestations of were observed here in this laboratory in a couple of decades ago. I'm sorry for the kind of longish quote, but I think that this is exactly what I want to say about this, so I'm going to tell it in just using the words of Casimir. So he begins with a kind of funny observation that low temperature physics was then and is today, but not quite today, a fascinating subject, but its fascination lies in the multiplicity of details rather than one major contribution to basic principles. That's a rather slighting compliment, I find, to low-temperature physics. He did write it before the discovery of DEC, which maybe even he would have counted as some major physics, not merely just tweaking around the edges. And then he has a paragraph which is, well, why is it interesting to go to these low temperatures? Heat, the thing we have when we're at finite temperatures, is a mode of motion. And one might expect that when the temperature goes to zero, all internal motion will cease, and matter will settle down to its true equilibrium. Why should anything very remarkable happen? And indeed, if atomic motion would follow the laws of classical mechanics, low-temperature physics might well be a dull subject. And that's, in fact, one thing that's true. That if you cool down, there are many things that you cool down and it's completely uninteresting. If you cool down a grain of sand, it just gets to be a cold grain of sand. And really nothing about its physical properties changes, no matter how low you make the temperature. It's true also of many metals. If you cool down copper, pretty much nothing interesting happens to the electrons in copper. It gets to be somewhat more conductive, but go to whatever low temperature you want, nothing interesting happens. But there are cases where there are interesting things, and he then says, but low temperature physics is quantum physics, and that is what makes it interesting. It means that there are discrete quantum states when the temperature goes down. States of higher energy will no longer be excited. Fewer and fewer states will be involved in the thermal motion, and this will reveal their true nature. So the idea of a true nature, something you finally reveal after all the noise of random atomic motion disappears, that some substances, some devices, have profoundly new and interesting kinds of behavior. And this turned out to be true of helium itself. That helium is a unique material that, it liquefies, and then you would say, well, at some lower temperature, it solidifies. And for every single material, except for helium, all of these eventually also solidify. They also finally make solids, not just liquids, but helium never solidifies. It remains in a liquid state all the way to absolute zero. And we're quite confident to say that no matter what the temperature would be, it would remain a liquid, and it has many really quantum properties, which I don't think I will tell here, but let me mention that among its various properties is one that's actually appropriate for refrigeration again, in a very different sense, because it has also the unique property that it's two isotopes. Helium has a heavy isotope, helium-4, and a light isotope, helium-3. And at low temperature, they both remain liquid, but they phase separate from each other, even though they're just isotopes. They're only different isotopes of each other. This does not happen in any other liquid. Water consists of hydrogen, which is some fraction of so-called heavy hydrogen, but it doesn't phase separate into heavy hydrogen water and light hydrogen water. It remains all mixed. But at these temperatures, but you have to get finally below 1 degree Kelvin before this begins to matter. But at that point, there's a separation in phase between the basically condensed helium-3 and another superfluid, which is also a so-called superfluid, which is very dilute in helium-3. And so there's an evaporation process that can take place in this two-phase region, that helium-3 can evaporate from this dense phase into the low-density but other liquid phase. And that provides a basis for a new stage of refrigeration. It says that these temperatures far below the liquefaction temperature of any of these liquids, another phenomenon, another interesting another thermodynamic phenomenon occurs that permits refrigeration down to these levels. And so this effect, which was, now we're coming rather closer in time, in the 1950s it was realized that this behavior would occur in this sort of final material liquid of helium. And and it would provide the basis of refrigeration. And with the right pumping and sort of still action, still like a distillery still, you could get all the way down to very small fractions of a Kelvin, maybe 0.01 Kelvin, based on this phase separation. All right, now I've told you all the sort of basics of this technology, or of this phenomenon of condensation. How is it used? So now I come right to the present, that this has provided the basis for making instruments that take structures to these temperatures, to a few millikelvin, to 5 or 10 or 15 millikelvin. And but what's really different now, compared with even 5 years ago or 10 years ago, is that these have become rather routine instruments even. And so here's a picture of an instrument that you could buy from a company, the Blue Force company, that basically reenacts all these events of low temperature physics, liquefaction of air and so forth, all in one package, rather big, largish package, with one push of a button. So this is the innards of this refrigerator, and up near the top is the, there's some gas handling that involves nitrogen at its liquid temperature, but immediately there's a stage that involves the liquefaction of helium, so there's a 4 Kelvin stage. But then down below are all the effects that were painstakingly understood here, and this is actually the still for the helium-3, helium-4 mixtures, the so-called dilution refrigerator part. And so this plate, notice a scale of about a meter, gets to a temperature of 10 millikelvin. And so all this effort, I mean, this was all done in the service mostly of low temperature physics itself. But this has turned out to be a necessary effort in order to accomplish the next stages of how we use bits. And in this cold state, bits can exhibit new phenomena, quantum phenomena, and can act as quantum bits for the possibility of realizing quantum computers. Now I'm going to say just a few words to close up about what that even means. I will barely do more than just say some of the words. That the concept of a so-called quantum mechanical computer can be traced, at least in some ways, to ideas expounded by Richard Feynman, and these are some clips from a paper that he wrote. I'm not going to decode for you. That's right, I was warned, don't show any equations, so this is just for fun. To say there are indeed equations somewhere behind this. He introduced some lines of thought that have been very profitably picked up. And I have here pictures of some current workers. I have to confess that one of the reasons I put up some of these current workers is to prove that the hegemony of the male scientist has finally been broken in our current era, I think. And that some of the absolute leaders of this field are not only of the, sorry to say, white male variety, but specifically the ideas that were picked up involve specific concepts for quantum computation, for ideas of quantum complexity, branching off from techniques of computer science, and ideas of error correction. But in fact, the field has been blossoming since the 80s and 90s, and ideas have been taken far beyond the speculations that Feynman introduced. Actually, Feynman was not really even the first. It is worthwhile to give credit to work of an earlier scientist, Steve Wiesner, who actually introduced a concept that harkens me back actually to the work of Huygens and the whole idea of polarization, because he introduced an idea which is one for changing the serial numbers of currency and making them quantum mechanical. And what he had in mind for that was a physical banknote in which was embedded particles, individual individual particles, but it's expressed as saying individual quanta of light, and that you would actually use the polarization of that light, of those quanta of light, to store serial numbers in a new and unbreakable way. But the real concepts of quantum computers, I mean, one cannot give a lecture about quantum computers without acknowledging that the big breakthrough was indeed the introduction of fast algorithms, but I really can't say very much about this. But the discoveries at Bell Laboratories in the 1990s by Shor showed that quite important computational problems, important for cryptography, and what's illustrated here is the arithmetic statement, this huge integer times this other huge integer equals this even huger integer. And, but the hard part is if you're given this integer, how do you find these factors, these prime factors? And the quantum procedures for doing that are understood to be very much more efficient than any classical procedures for doing that. Now, on the basis of that, quantum computers are beginning to be built. So I know I've talked to people who, pictures like these are seen in the press. There are some organizations like Google and IBM that have announced, advances and breakthroughs in making quantum computers, and you'll see pretty pictures of this whole thing, and say, there's IBM's or Google's quantum computer. But mainly I look at it and say, no, that's IBM and Google's refrigerator. Like, where's the quantum computer? And it's not, this is an uninstalled case. This is actually an instrument for a quantum computer, but the quantum computer itself is just a chip that sits in a rather unassuming can right at the bottom when it's actually in action. I don't think they ever really clarified that, but this whole thing is the infrastructure of making the quantum computer work. The quantum computer itself is actually a microchip, just like our regular computers are today, at least in the embodiments that are being studied by these companies. And this is indeed a picture of, this is a picture of, a chip on a silicon wafer, and here's some, microelectronic patternings on it. It uses some of the physics of superconducting metals, and it's a structure with 16 qubits. I can pick them out by eye. There are these sort of squarish regions in a row here and in a row here, and then there are all sorts of control structures around them. For these to work, they involve many resonance structures, so this is like an incredible musical instrument of some kind with 46 strings, you might say. They all have incredible high quality factors. In other words, if you pluck them, they keep going for 10 million oscillations before slowing down even at all. And some of these are details I shouldn't really go into, but all this is only possible if when everything else is kept almost perfectly still, meaning the temperature is indeed 0.02 Kelvin of this chip. It's not especially miniaturized, I would also say. This is a 1 millimeter scale bar. So if you look at a comparable micrograph of a CMOS chip, the ones in your phones or something, the feature size is much, much smaller, actually. And but at the current stage of development anyway, this is what's known to do, that you can do. And this is of, I would say moderately good functionality, not super great functionality. And there are still many struggles in how to turn this into a more advanced product. But IBM is already offering it for use for people in the world. You can go on the cloud and try out some small runs on this tiny 16-qubit machine. So I'm basically ready to close. I haven't actually told you much about what we've got a quantum computer, and here's how it works. We don't really know. I actually say we have kind of a quantum computer. It's kind of the data general version. And it's some little fish, and it's going to get swallowed by some other fish, I'm pretty sure. I think that this particular chip will be something totally obsolete in some not very distant future. And what exactly it will be replaced by, I don't exactly know, but it will be something that works better, I guess. So let me close it up. The struggles that are taking place right now to sort of make more extended chips, this is just sort of a concept drawing of how this chip should look like when it gets to be of somewhat larger scale, is that even at these incredibly low temperatures and with all this control, they still don't work so well, and so Feynman himself recognized that we will need things like error correction codes of a much more advanced sort than we've ever had for dealing with the still residual noisiness of these systems. That's one area of research that's being covered quite thoroughly in the summer school in these weeks. So let me just circle you right back to the beginning. So, well, what should I leave you with here? These tales of how we get to where we are today stretch back, far back into the past. You know, I've easily stretched you 300 years back into the past, but of course that's not actually the beginning of anything either. Science and technology will continue interacting, sometimes uncomfortably, but with, causing new progressions in areas, and definitely in this quantum area that will be happening. And I've offered you 2 books for summer reading, the Tracy Kidder book, and I also offer you the Hendrik Casimir book, if you want to do some interesting reading about these things. So that's all I have to say. Thank you. Yeah, good question. So the question is, I make a big deal out of cooling, and couldn't this all be done without cooling? In some pretty fundamental sense, no. That is, some technique of cooling is definitely needed, because the states that we need to use for computation in quantum computing, we need basically perfect control over them. So they must not be subject to, injection of energy and removal of energy, which the normal thermal agitations would occur, would cause. However, that's not quite the same as saying we need this, big machine that will cool a macroscopic chunk of material like a chip to these incredibly low temperatures. And in fact, it was proved here by Lyman and Cornell in some sense that they had apparatuses that fundamentally were just sitting in the laboratory, but it was the lasers that were causing some little bit of something to cool, not even a macroscopic piece of thing, just a small collection of atoms were cooled in their experiments. Now, maybe we would be smart enough to figure out how to do that in these devices as well, but maybe not. I mean, it's very handy that you can make this whole macroscopic, this actual chip. You could in fact put your whole phone into this refrigerator, and the whole thing would be at those temperatures. And that's a little bit like what this is. So it's trying the kind of brute force approach, saying if some of it has to be cold, let's just try making it all cold. But for sure, some aspect of it has to be cold. So the user interface of a quantum computer is a classical computer, and your interface will be a keyboard or something. So it's actually not so different. That is, you pose the problem to the quantum computer, like find these factors. It goes and does its quantum stuff, and then it tells you the answer in ordinary language.
Is a quantum bit still a two-state bit?
Yes and no. Okay, where do we go with that? It does need some fundamental dichotomy, like polarization is either ordinary or extraordinary in the language of these calcite crystals. It's either vertical or horizontal. But in polarization and in other instances of quantum bits, you're allowed to make superpositions of them. That is, where they're simultaneously, in the sense of waves, you can put them in superpositions of both attributes attributes at once. So you can have something that has a component that's polarized this way and a component that's polarized this way. And that's what gets split if you send that light into this crystal. So the idea that it has the possibility of superposition is what's important and unique to quantum bits. But the dichotomy is still there. The idea you have to have a dichotomous physical, object.
A couple fundamental questions. How did you know that the temperature achieved in these experiments was 0.01 degrees absolute?
Dave, how do we know that?
RUROX is ruthenium oxide resistors that change their resistance with temperature, so you can measure that resistance.
Okay, the answer is you have a thermometer. It's real tricky to have thermometers at these
I've tried to do
temperatures.
this before, and so the question is when you measure that resistance, how do you do that without heating the resistance up?
Very weakly, I think. It's a really small resistor, and you only put a teeny amount of current into it.
Next question is the single photon, what wavelength is it at?
Well, it can be at any wavelength, but in these particular examples, for example, in this chip, there are photons running in and out of this and being passed around. They're at microwave oven frequencies, 5 gigahertz or 10 gigahertz.
Okay, right. So when you pass one out and it's not oscillating somewhere within the chip itself, how does that not cause a heating effect? It's got to be absorbed, or is it just passed away so far away?
Well, even at that level, the introduction and then controlled removal of energy is done even at the level of the energy of one single photon. So yes, sometimes you add energy, but you have a complete accounting of it. It's not random in any sense.
Way in the back.
What kind of questions are scientists asking quantum computers?
Yes and no.
Okay. I thought the question was what kinds of questions are okay.
Scientists asking of quantum computers. What are the kinds of questions that these computers are answering?
Okay, fair question. They're not necessarily the ones we'd like them to. I mean, we'd like them to balance our checkbooks better or something like that. But instead, they say, no. Here's a list of things that I can do well. I mean, embodying, pretending the quantum computer is personified. One is problems in certain areas of mathematics, like finding factors of numbers or other number theory questions. The other areas tend to be ones that are themselves closely related to quantum physics, like how do you, by computation, simulate what a molecule will do, or how will it bond together? So problems of so-called quantum chemistry, and so there are concepts of how to program the quantum computer, how to use algorithms on the quantum computer that will answer those kind of questions. So that's a list. We'd like it to be a long list, but sorry, it won't balance your checkbook.
And I think we have time for one more question.
So, the idea of cooling is still getting in my way of really thinking of what kind of device that we will be able to utilize, all of us, rather than it being in some remote location with a lot of energy sink.
Yeah. Well, because that's what we do all the time today, right?
That's not right, we do that. But, that seems to limit, and I'd like you to talk about, what are the bounds on that and the energy that has to be put into that.
Yeah.
And then number two, there's some quantum work at Amherst, and I'm just wondering.
Sorry, there is some what?
There is some quantum work at Amherst.
Oh, okay. There's some quantum work at what, sir?
And the ambient temperature.
Oh, an ambient temperature, yeah.
As you pointed out,
Okay, yes. Well, I don't know. How can I even begin to answer that? I mean, some of this work.
Okay, what's the question?
Well, I'll first try to answer the question of have we gotten any control over our energy use in computing? The global answer is no, right? That we're building, Google and other organizations gigantic factory-sized things with factory-sized energy consumption to service, you know, your query needs or whatever you use your box for.
So it doesn't seem a limit to you, this.
This research did emerge to a large extent from asking fundamental questions about that, about asking if you have a given computational problem, what is the minimum energy actually required to do those computations? And that was one of the things that led to quantum ideas for computation. Now that hasn't meant that we haven't solved the energy problem, but we at least have a better concept about it now by doing that work. Our ability to solve the problem of the energy use of information technology is, well, not soon, I fear to say. I agree, or it is absolutely true, that there are quantum phenomena all around us and you know, ambient conditions. How to really harness them and use them for controlled processes like precise computation, that we really don't know how to do.
And since we started late, if there's a couple more questions, I saw one in this region. You, sir.
I was wondering about the things the next advance in the actual qubit is going to be with these resonators, or do you see it moving towards more like a plus quantum charge?
There are a lot of things that are in play today. So what I've shown here are one species of possible solid-state computer, and there are about 5 other kinds that are possible that involve either like atomic impurities in crystals or other kinds of quantum dot devices, and then there are ones from atomic physics, and suspended atoms and traps. We are in an era, I don't know, to me it's like when cars started being built, and there were, you know, the first 10 years of cars, there were all sorts of weird models, you know, and finally the internal combustion engine, you know, turned out to be the winner. We're kind of in that early stage.
And we had one more here.
You say 3 quantum bits stored to the power 3 information. So how do we get particular information to be used in the process for that?
Well, yeah, okay. The question is more or less, and this is from the point of view of some knowledge of quantum physics, that if you have n bits, then you have like 2 to the n computations that are available. It is, however, true that when you actually want to bring the information back to the classical world, you have to kind of commit yourself, and you'll only get n bits you'll get an n bit number out of that computation. So the power of quantum computation comes before that it comes from sort of interference of different pathways of computation. I don't know if that's so helpful, but at this moment I shouldn't give more than a brief answer.
With that, let's thank David again.